All right, welcome to part 2 of section 7.2. I actually meant to finish the last example in part 1. I forgot about this part, so let's get this out of the way. Let me just double check the instructions. I think I know what they were. Use properties of logarithms to simplify this expression. Okay. 1 second. Okay, I had to dig that window back out. All right, so this is a pre-calc problem, really. So we're going to use our properties of logarithms, our product rule, quotient rule, power rule, to combine this into a single logarithm. So let's see, I think the first thing we should do is rewrite that cube root as an exponent. Hopefully you remember that cube root is 1/3 power. All right, now I see a quotient rule coming up here pretty soon, but before we can use the quotient rule, we have to take care of this 3. So what I'm going to do is use my so-called reverse power rule for logarithms. Instead of it's, all right, so that is the same thing as natural log t squared minus 1 to the 1/3, and now that whole thing is cubed, and I think you can see where that's going. Right, because when you do a 1/3 power to a 1/3 power, those exponents just cancel each other out. So now we have natural log t squared minus 1 minus natural log t plus 1. So now we can use our quotient rule and write that as natural log t squared minus 1 over t plus 1. Now, I've actually been thinking about this example quite a bit since recording part 1, and I want to be very careful with what I do next. So please notice that in the original expression, let's see, looks like the domain of that original expression would be, oh gosh. Well, on the one hand, you would need to have t plus 1 be greater than 0. I might be overthinking this. And that would mean that t is greater than -1. On the other hand, you would also have to have t squared minus 1 be greater than 0. Right? And I don't want to get too far out in the weeds here with fooling around with a math C polynomial inequality, but basically t squared greater than 1 would mean that t is greater than 1 or t is less than -1. So now this and this both have to be true in order for this expression to be defined. And if you think about it, the only way that you're going to have t greater than 1 or less than -1, and at the same time also have t greater than -1, that would mean that t would have to be greater than 1. So that is the domain of the original expression. And the reason I mention that, and again, this may not even come up in the homework, I'm just being overly cautious. You may have noticed that you can simplify that t squared minus 1 over t plus 1, because of course t squared minus 1 is t minus 1 t plus 1. All right, so now I can get rid of my t plus 1s. Oh, never mind, we're good. Okay, I was just going to point out that the simplified expression should have the same domain as the one that we started with, and it does. So we're good. This expression simplifies down to natural log of t minus 1. All right. Better safe than sorry. Okay, so let's go back to the presentation and let's talk about integrals. All right, so give me just a second here. There we go. All right, so in part 1, we talked about the differentiation rule for natural log absolute value of x. All right. The derivative of natural log absolute value of x is 1 over x for all x not equal to 0. So this is the backwards version of that rule. And what drives students crazy is when you integrate something of the form 1 over u du, the u in the answer has to go in absolute value. Okay, so just remember that. And of course, because it's an indefinite integral, you need that plus c. I like to joke a lot about the plus c. No points if you forget the plus c. Just kidding. Okay, so now let's look at some examples of using that rule. So I have these 2 examples. I noticed when I was preparing this yesterday that I kept numbering my examples 1 and 2, 1 and 2, 1 and 2. So hopefully that doesn't get confusing. Okay, going back to the tablet. Okay, here we are. So we're integrating r over 4r squared minus 5 with respect to r. All right, so I hope you remember substitution. At this point, that's just about the only integration rule we know. That's about to change pretty soon. All right. So you remember how substitution works. You look for a function and then look for something that looks like its derivative. Now, I have noticed from teaching Calc 2 many, many times before that I may not write out my substitution problems the same way that your Calc 1 instructor did, and that's fine. You know, as long as what you do is correct and we end up with the same thing, that's what's important. So in this case, we're going to let u equal 4r squared minus 5, which would mean that du is 8r dr, right? But I don't want an 8r dr. I just want an rdr. I can't say that without thinking rdrrr. Sorry, I had to get that out of my system. So the way that I deal with that is I divide both sides by 8, which means that when I go to replace this r dr, it's going to be replaced by 1/8 du. So this integral, the 4r squared minus 5 is going to be replaced with u. And then the r dr is going to be replaced with 1/8, which can go out here, du. And hey, that looks familiar, right? That's what we just went over. The integral of du over u is natural log absolute value u plus c. And then I have a classic Mitchell joke that I always use here when you're using substitution. Remember to write the answer correctly, or as I say, this isn't about u, right? In this case, it's about r. So we need to back substitute and replace that u with a 4r squared minus 5. And there it is. So the integral r over 4r squared minus 5 with respect to r is 1/8 times the natural log of absolute value 4r squared minus 5 plus c. All right, next we have this one. This is a definite integral. The integral from 2 to 16 of 1 over 2x times the square root of natural log x with respect to x. Now, I have a certain way that I love to do integration by substitution when it comes to definite integrals. Your Calc 1 instructor may or may not have done this, but I swear by it. So I'm going to show you what I'm talking about. All right, so in this case, let's see. We're going to make u be a natural log of x. And then, of course, du will be 1 over x dx, which is almost what we have, right? So what takes up the rest of that integral, other than the square root, which we'll worry about in a minute, is that 2 on the bottom. So if we just multiply both sides by 1/2, we'll get 1/2 du is equal to 1 over 2x dx. All right, so I think we're in business. So this integral is going to become, let's see, 2x, or 1 over 2x dx is going to get replaced with 1/2 du. And then natural log x gets replaced with u. Remember the square root, so that's going to go there. Okay. So what I like to do with my definite integrals when I'm using substitution is I like to actually change the limits of integration. So in the original problem, these are x values. You can actually change them into u values. And the advantage of one advantage of that, there are a few. One advantage of that is that then we will not have to go back to x. All right. So how do you calculate the new limits of integration? Well, you just plug them into the equation that relates u to x. So u is equal to natural log x, which means that when x is 2, u is natural log 2. And when x is 16, u is natural log 16. So the new integral is going to go from u equals natural log 2 to u equals natural log 16. And now I can forget all about x because remember that a definite integral evaluates to a number, all right? And so that this will give us the correct number. So how do you integrate du over the square root of u? Well, that's something you learned in Calc 1. All right, please don't tell me that that's natural log square root of u. It is not. All right, what you want to do with this is rewrite it as u to the negative 1/2 du, and then use the so-called backwards power rule. Remember how the backwards power rule works? Add 1 to the exponent, divide by the new exponent. So why don't we say u to the 1/2 divided by 1/2, or you can multiply by 2. And then eventually we will plug in natural log 16. We will plug in natural log 2. I have a feeling this is going to simplify to a nice pretty number maybe. All right, so look at this, 2 times 1/2. We can just get rid of those. Let's go to the next screen. So we have, and I already forgot what that said, u to the 1/2, plug in natural log 16, plug in natural log 2, which is going to give us the square root, or now let's do it like this. Natural log, 16 to the 1/2 minus natural log 2 to the 1/2. Oh my goodness. I almost fell into a trap that wouldn't have been good. So if you're looking at that and you're wondering, can I simplify that? Well, think about your power rule. Think about what the power rule for logarithms looks like. If that first term was a natural log 16 to the 1/2, then you could do, and you could put the 1/2 outside. But if the whole natural log is to the power 1/2, then you can't do that. However, I am determined to simplify this answer. And by the way, when you're doing your online homework, my recollection is that your online homework is not super picky about the form of your answer. So if you don't simplify your answer quite as much as I do, it may be okay. All right. But here's what I noticed. 16 happens to be a power of 2. Okay. So why don't we write this as natural log of 2 to the 4th. And then I still have to be super careful with the 4 next to the 1/2. That is not going to give you a 2. All right, because this 2 to the 4th right here is inside the logarithm. Okay. But what I can do is this. I can take the 4 and go, and that's going to become 4 natural log 2 to the 1/2 minus natural log 2 to the 1/2. And now let's remember that 1/2 power is a square root. So when you take the square root of 4 natural log 2, you get 2 times the square root of natural log 2, don't you? And then this over here is just square root natural log 2. So this answer does eventually simplify down to just the square root of natural log 2. So I think that's kind of nice. Okay. Nicer than if we had left it like this. All right. Okay, so let's see what's next.